In this video, we will be discussing how to calculate visibility between a ground vehicle and spacecraft by reviewing the Grand Canyon Ground Vehicle Visibility Sample Mission Plan provided with FreeFlyer. The Grand Canyon Ground Vehicle Visibility Sample Mission Plan demonstrates the use of the terrain object for visibility analysis with ground vehicle objects. Visibility analysis is conducted between two vehicles on the ground and a GPS constellation overhead. As you'll notice, one of the ground vehicles follows a route deep within the Grand Canyon, while the second ground vehicle follows a similar route on a plateau next to the canyon. In the output screen, you will see plots and visualizations that demonstrate that the vehicle outside the canyon is able to see more of the GPS satellites in comparison to the vehicle that is in the canyon throughout the propagation. First, we will walk through the script to get a better understanding of the objects and variables that will be used throughout the mission plan. In Freeform 2, which is labeled as Define Variables, all of the variables, strings, and arrays are defined. The first two strings, FilePath1 and FilePath2, are KML files which are stored in the Support Files folder. These files store latitude and longitude values which will be used as the ground vehicle waypoints for propagation. We will refer back to these files when we take a look at the Setting Up Vehicles freeform block in a little bit. Next, we have defined a few different lists. Lists are a container for one or more FreeFlyer objects of the same type. In this script, the first two lists are lists of visibility segments, and the second two are lists of vectors. These objects will be used when calculating the visibility between the ground vehicles and spacecraft later on in the mission plan. Next, we have a list of variables which are used for analysis with the ground vehicle object. The prop stop, step size, and ground vehicle speed variables are used to define how long the propagation for the ground vehicles will last and how fast the ground vehicles will go during that propagation. The arrays lat in canyon, long in canyon, lat on plateau, and long on plateau are used as containers for the latitude and longitude values of the ground vehicles, which are pulled from the KML files. Finally, the variables in the Region of Interest block define the latitude and longitude points, which are bounds associated with the terrain file being used. We will talk a little bit more in depth on these when we take a look at the Setup Terrain Points freeform block. Now we will take a look at how the terrain points are set up in the mission plan. In this mission plan, the terrain is being visualized as a point group object, where the number of points in the point group are calculated based on the point spacing variables shown in Freeform 2. Once we calculate the number of points based on point spacing, we assign that value to be equal to the number of points in the point group. Next, using a for loop, we set the position and elevation for a grid of points based on the minimum and maximum latitude and longitude values set in Freeform 2. This for loop iterates through every point in the terrain file and sets the latitude and longitude based on the lat and long arrays. It also sets the value for the height of the terrain using the terrain.getHeight method. Finally, using the Color Tools Interpolate Color RGB method, we color the points based on their height, where the lowest points are colored black and the highest points are colored white. For more information on implementing terrain into FreeFlyer, please take a look at the All New Terrain Modeling in FreeFlyer blog post, which is published on our corporate website. Next, we will look at how the ground vehicles and the GPS formation are set up in script. As mentioned earlier, the ground vehicles use ground waypoints as the source of propagation. The Convert KML procedure, which is a procedure included with your FreeFlyer download, converts the latitude and longitude values stored in the KML file into ground waypoints so that they can be used as the source of propagation. The paths used in this mission plan were both drawn in Google Earth and were saved as KML files so that we could use the Convert KML procedure to convert the latitude and longitude values. As you'll notice, the path that's drawn in Google Earth is identical to the path in FreeFlyer shown in the 2D map. Next, both the ground vehicle in canyon and ground vehicle on plateau are initialized using the first value of latitude and longitude stored in their respective arrays, and both are set to have a height based on the terrain at that latitude and longitude using the terrain.setHeight method. Finally, at the bottom of this freeform, we step the GPS formation to the ground vehicle's epoch so that our epochs are synchronized. Now we want to set up our visibility segments and vectors that we defined in Freeform 2 so that we are able to perform some visibility analysis. First, we want to set the count of all of our visibility segments to be equal to the number of spacecraft in the GPS formation. This is done so that we can analyze and visualize the contact between the ground vehicles and every spacecraft in the formation. Then, using a for loop, we define the targets and observers for each of our visibility segments. Iterating through the for loop allows us to condense our code so that we are not reusing the same lines of code for each spacecraft in the formation. For the segments in the canyon, we set the target to be the ground vehicle in canyon, and for the segments on the plateau, we set the target to be the ground vehicle on plateau. After that, we want to set the observer for both sets of visibility segments to be a spacecraft in the GPS formation. Once we have set the targets and observers, we add Earth as an occulting body using the add occulting body method. When using terrain in your visibility analysis, the next line of code is the most important. In order for your code to pass syntax check, you must set the celestial object occultation model equal to 1. This is because the Earth must be modeled as an ellipsoid for your mission plan to run visibility analysis with terrain. Finally, we add the Grand Canyon terrain as our occulting terrain. If you had more than one terrain files to use, you would simply add them here by using the add occulting terrain method. Once our visibility segments are set up, we can then build our vectors for visualization. Using the build vector method, we set the first argument to be 9 so that it builds a vector from one object to another. These vectors are being drawn from the individual spacecraft in the formation to both respective ground vehicles. After the vectors are set up, we give them each a color and add them to our 3D view. Before we run the mission plan, the last thing we want to take a look at is the propagation loop. Here we will see what is calculated while our ground vehicles and spacecraft propagate from the ground vehicle and canyon's initial epoch to the variable prop stop, which we defined in Freeform 2. Within the while loop, the first thing you'll notice is that we are collecting the heights for both ground vehicles throughout the propagation, which will be displayed in a plot window on the output screen. Next, we check for visibility between the GPS satellites and the ground vehicles. We do this by iterating through a for loop and utilizing an if loop to check to see if the visibility segment.visibility method is equal to 1. The visibility method checks for line of sight contact at each step, and if there is visibility, the outputted value is equal to 1. So, if there is visibility, we increment the numGPS context variable so that our plot will be updated and also activate the vector between the spacecraft in the formation and the ground vehicle. Next, we update our contact plot, height plot, 2D and 3D views. We then step the objects and synchronize their epochs so that all of our calculations are accurate. Lastly, we reset the GPS contact count so that our contact plot is updated accordingly in the output window. Now that we have gone through the whole script, let's dive into the output. In the top left view window, you can see the 2D map with the ground vehicles driving through and on top of the canyon. As mentioned previously, the point group is colored based on the height of the terrain at each latitude and longitude value, where the black points are the lowest and the white points are the highest. As the ground vehicles traverse, take note of the plot in the top right corner. The plot in the top right corner shows the height in kilometers of each ground vehicle based on their current location of the terrain. You'll notice that the light blue line, which represents the ground vehicle in the Grand Canyon, consistently has a height which is lower than that of the ground vehicle on the plateau. In the bottom right corner is the plot which shows the number of GPS satellites in contact with each ground vehicle. As you would expect, the ground vehicle that is inside the canyon typically is in contact with less spacecraft than the ground vehicle on the plateau. This is because the ground vehicle that is inside the canyon is typically surrounded by terrain which is blocking the line of sight contact. Finally, in the bottom left corner is the 3D view window. The 3D view window is a visual representation of the contact plot. Here you will see the vectors from the spacecraft to the ground vehicles turn on and off based on whether or not there is contact between the spacecraft and the ground vehicles. That completes our walkthrough of the Grand Canyon Ground Vehicle Visibility Sample Mission Plan. If you have any additional questions about this sample mission plan or anything Free Flyer related, please feel free to reach out to our tech support team at techsupport@aisolutions.com or by phone at 301-306-1756, extension 2. We hope that this has been a helpful walkthrough, and please keep an eye out for more videos in the future. Thanks for watching.